Hello, good morning. Welcome to lecture number 4 on blockchain introduction, including evolution, types, features, challenges, and more. This is probably the last not so technical lecture before we dive in into all the mechanisms. Okay, so let's start with the evolution. People are saying that there have been 3 to 4 types of blockchain. So they denote them as blockchain 1.0 to 4.0. So let's see what they mean. It all started, of course, with Bitcoin, the cryptocurrencies. So today we have over 13,000 public cryptocurrencies available. Of course, the mortality rate is quite high, so a lot of cryptocurrencies, new cryptocurrencies are popping up, but they are also fading out. So only around 9,000 are still active out of this number. Later, as mentioned around 2013, there came blockchain 2.0, which focused on smart contracts, but also started to introduce the topic of decentralized finance and non-fungible tokens. So we are going to spend significant fraction of the course speaking about smart contracts. So I'm not going to touch upon them right now. On the other hand, I would like to speak a bit about decentralized finance and the non-fungible tokens. So decentralized finance, or DeFi, is a financial system that uses blockchain technology to enable individual transactions or peer-to-peer transactions. So what do I mean by that? Traditionally, when there is a transfer of funds or documents or properties, it's done through intermediaries. Could be a government, could be a bank. In Norway, people usually do not buy real estate directly, so there is almost no direct interaction between the buyer and the seller. Instead, there is a real estate broker, and virtually all interaction, all formal interaction, goes through the broker. So for example, bidding, and at the end, when there is a time to sign the agreement, then one party needs to pay for the property, and the other party needs to transfer the ownership. So what happens is that one party deposits the funds to the broker, and the other party deposits the documents to the broker. And the broker does atomic swap, because obviously the order is very important. So the broker is assumed to be trustworthy, and the broker does the atomic swap. So the idea of DeFi is to replace such human-based brokers with the mechanisms, smart contracts running on blockchain. So what's the problem with human brokers? Well, first of all, they can look into your data. You don't really know what they do with your data. You know that, so they're trustworthy in the sense that they are not taking your money and they are doing their job. But they might be peeking in your data. So you're not sure about your privacy. Also, they store your data somewhere on their servers, but you don't really know how good their security are. So that's why, like on the other hand, smart contract is much better in that regard. Your smart broker code is transparent. You know exactly what it's doing, and even more importantly, you know what it is not doing. So that's the idea of decentralized finance. For example, we can announce like donations. So people would be collectively donating funds to a certain cause. That would be one example of decentralized finance application. Regarding non-fungible tokens or NFT, what is it? It's a unique digital asset that's recorded on a blockchain. What's, okay, how is it used? What kind of assets? In practice, NFT may represent several things. Well, they can represent a lot of different things, but most popular NFT are digital art. It could be paintings, drawings, poetry, books. So instead of real Mona Lisa or Taj Mahal, you'll get some virtual Taj Mahal, or some virtual representation of art. And it turns out that such virtual representation can sell out for significant amount of money. So what's important is that on blockchain, the ownership is very easy to establish, verify, and difficult to fake. So it's very clear who owns a particular piece of art. What's interesting is that the piece of art may actually be open to all. The blockchain can be open, so everyone can see the piece of art. What a person would be paying for is the ownership of that piece of art. Other examples, of course, collectible items, like, well, children like to collect cards with players of their favorite sports, so you could do it through NFTs as well. Virtual real estate, so you could have beautiful houses, virtual houses, and own them. Turns out that it's quite a popular thing, and a lot of people are interested. So that's why there was an NFT hype. There have been even analysis because, like, in some regards, virtual tokens, art, and similar can be superior to real ones. For example, you can be sure that they're never stolen, and that they never deteriorate with time, right? They do not require maintenance and restoration. So that's some of the reasons why it's popular among people. So that was, in terms of the progression and evolution of blockchain, that was blockchain 2.0. Now we come to blockchain 3.0. And if blockchain 2.0 came out with smart contracts, so at this point smart contracts were just developing, right? At 3.0, we already had a significant library of patterns and recipes for building smart contracts. And people started to build real applications. So 2.0 was more conceptual, and of course, like real smart contracts. But 3.0 started with practical applications, and not just based on smart contracts. And we call those applications dApps. So the concept of dApps was coined. And not only applications, there came out platforms for building and tools for building such applications, debugging such and testing. So some of the examples, one interesting typical example would be Ether tweet. So instead of Twitter, you can tweet, you can and then maintain microblogging on Ethereum. What's the advantage? One advantage is better privacy. So so there are some privacy related. You can be anonymous if you want as a blogger. It can be better integrated with Ethereum, so you can collect donations, for example, in Ether. And perhaps the biggest advantage is resistance or resilience to censorship, because it's on blockchain. So it's decentralized. There is always a question to what extent big platforms such as Facebook and Twitter, well now X, to what extent they censorship whatever people are publishing, right? And what they can be allowed to censor and what they cannot be allowed to censor. So that's a big debate all over the world. Now, in either tweet, it's impossible to censor. And not only this, if you publish it on blockchain, in blockchain you can only append, you cannot remove. So it's there forever. In that sense, it's resistant or resilient to censorship. That's probably the biggest advantage of either tweet. And this was just one example. And of course, there are many applications related, dApps related to crowdfunding, charity donation, forecast markets, and betting, and many others. So again, like betting platforms, it's good, or there are certain advantages in implementing betting platforms on blockchain because the bets are all visible and clear and transparent, and it's impossible to fake bets. Okay, so what's blockchain 4.0? Well, the truth is that no one exactly knows what it is. This is what people are saying, this is what's happening now. So it's the further or future evolution of blockchain, the trends in blockchain that happen today. So what's the focus in blockchain 4.0? Such as Ether tweet, but industrial scale, maybe business applications. And specific focuses on issues such as scalability, interoperability, and privacy. So we are going to have a dedicated, what is scalability? The scalability challenges are related to storage, how much storage in space an application takes. In terms of the number of participants, can the application run thousands or millions of participants? And also in terms of the throughput rate of transactions. How fast the application can process new transactions. And regarding privacy in blockchain applications, we are going also to spend some time talking about the use of zero knowledge and other techniques. And we'll see more on that in the lecture on digital identity. So I'm not going to expand on this now in this lecture. However, I would like to talk a bit about interoperability. As the blockchain platforms are developing, we are now witnessing a proliferation, right? And there is also some competition. So every blockchain platform, maybe not every, but many blockchain platforms are trying to create their own ecosystems and lock their users and applications to that particular blockchain system. This is not good for the applications. This creates silos, which means that users are sort of wedded to a particular blockchain platform. They cannot benefit from other blockchain platforms. And this is why the topic of interoperability between blockchain platforms, so the topic of interoperability between different blockchain platforms becomes so important. So what is interoperability? Interoperability means that if I own Bitcoin, I should also be able to pay on Ethereum. I should be able to convert cryptocurrencies. That's one aspect of interoperability. Other aspect of interoperability would be data. If my data is stored, on one blockchain platform, it should be visible on other blockchain platforms as well. There could even be some transactions which are cross-platform. So this is the main topic in that context. So people have been building bridges between competing blockchain systems. And another challenge is, again, the atomicity. Please recall the example about a real estate broker I gave you previously. When you buy products, and so the seller and the buyer do not even see each other, right? So what's the order of operations, right? So if someone buys first, how can that someone be sure that the seller would provide the services or the goods? If the seller sends the goods first, how can the seller be sure that the buyer will pay for it? So the order is important. And atomicity means that the several operations occur or take place together as part of a single transaction. So that's the meaning of atomicity, and it's very important property and feature, guarantee in distributed systems. So when we have two different blockchain systems, how can we guarantee that atomicity? That's not a simple problem. So there have been attempts to develop solutions for atomic swap of cryptocurrencies. Okay, so far we've been talking about blockchain evolution. Now, let's a bit talk about research challenges, which are characteristic of each step in the evolution. So we study blockchain for a number of reasons. We know like advantages, right? We know blockchains resist censorship, avoid the brokers, the middleman, the intermediary, provide transparency, and therefore reduce fraud, and may also minimize redundancy. So, but there are also interesting research challenges in that regard. So from the beginning, there was an attempt that, like, there have been many efforts to identify different security flaws. At 2.0, there started the challenge of verifying smart contracts and creating middleware services. For 3.0, there was a focus on scalability and the speed of the operations, data privacy, and correctness of data entry points. Now, let's talk a bit about different types of blockchain systems. So, the very basic taxonomy is who can read data in the blockchain and who can perform update operations on the blockchain. So the options are quite simple. So anyone, the read access is open to all, or read access restricted to specific identities. And that regarding updates, so either anyone can propose updates or update access is also restricted by identities. This is quite an important distinction, right? So we have 4 different choices. And it turns out 4 different combinations. It turns out that all 4 combinations are meaningful. There are systems that correspond to each combination. There are applications for which this is the combination they would like to go for. Okay, so let's see. Suppose, like, the case anyone can propose updates and anyone can read. Well, that's the basic cryptocurrencies, such as Bitcoin and Ethereum. And it's suited for cryptocurrencies and NFTs. The other end of the spectrum is full restriction. Both read and write accesses are restricted by identities. So there are systems that go for that. All Hyperledger projects, including Corda. And it's actually my belief that most practical applications would use this type of, basically most practical applications do need some kind of access control. Whether it's healthcare, whether it's supply chains, whether it's energy trading, and so on. So, so there are specific exceptions when it's not suitable, but I believe that this case is suited for most applications. But there are two other interesting cases. One case when anyone can read from the blockchain, but only selected few can update the blockchain. And Ripple works in this model, which is also a cryptocurrency. So what applications would it be suitable for? Well, for example, government financial records. So government financial records, the idea is that they should be transparent, right? There are some documents that only the government can produce, but anyone can read. So transparency is important. And well, this is just one small example, government financial record, but you understand the principle, right? So it can be extendable to any other cases when we need transparency for documents which are produced by selected few. And the other interesting case is when we do not impose a restriction on updates, but we do impose restrictions on read accesses. So when would it be important? Voting. So voting, everyone can vote, but not everyone should be allowed to see the exact results, who voted how. And then there are systems that support that. So Ethereum, the main deployment of Ethereum falls here, of course. You can also have proprietary deployment of Ethereum, which could be configured to support that case through smart contracts. Now, of course, in this case, you don't need any control over identities. In cryptocurrencies such as Bitcoin and Ethereum, the identities are represented by public keys. So you don't know anything the system doesn't know anything about the real identities of the participants. In all other cases, the system needs to know the identities because that's the only way they can do access control. So, so that's the most meaningful terminology or taxonomy in my view. So the above is well defined, but it has no commonly associated terminology. And general public, instead we have a lot of different terms, such as open, closed, permission, permissionless, public, private, and there is more. So there is a bit of confusion, right? What these terms refer to. Well, usually permissionless means that there is some sort of control over identities. And I made the emphasis on usual because, if you see a lot of a popular science article and journalists, they do not necessarily correctly use all those terms. So when you read, you should be careful. Open-closed, public-private, right? So open-closed usually talks about read accesses, while public-private usually talks about update accesses. But of course, like this terminology is a bit confusing. It's not evoking any direct associations in a way. Apart from that major taxonomy, we can also talk about other types. So another dimension of taxonomy would be decentralization and scale. We have centralized systems. We have large-scale decentralized, and we have medium-scale consortium blockchains. Now, centralized blockchain is pretty much a misnomer, because if you only have like one entity controlling the updates to the blockchain, then there is no practical reason to use blockchain in that case. Blockchain is about creating decentralized trust, right? And decentralized trust can only needed to be created between participants who are not trusting each other. Now, if you have only one participant, that's a trivial case, right? So why would you go for blockchain? Database is usually more efficient and more compact in terms of storage. So sometimes it's just used as a keyword, as a buzzword. However, the cases of large-scale decentralized systems and medium-scale consortium blockchain are absolutely viable setups. And we'll see quite a few applications related to each. So different blockchain types also have different corresponding models with respect to how we manage the identity of the participants, how we authenticate the participants, what exactly the trust between the participants are, and what kind of attacks we can expect. Because attacks in a consortium model would be different from attacks in an open blockchain. Let's talk a bit about blockchain key features. So blockchain provides immutability so I'll talk about immutability soon in the next slide. Blockchain may provide transparency because if the ledger is open, it's open for all. Verifiability, decentralization of trust, and in some cases, for some systems, it may also provide anonymity. And of course, there are a lot of security features baked in. So those are contributing to the benefits of blockchain. Now, let's talk about immutability a bit more. So, as mentioned, blockchain and chain of blocks, which are cryptographically linked to each other. How are they linked? Well, each block may use a cryptographic pointer to the previous block. So what is a cryptographic pointer? It includes a pointer, and it also includes a hash of the previous block. Now, what's the idea of this construction? The idea is that suppose the hacker somehow managed to hack block 2. Block 0. Okay. But we talked about hash functions last time. So even if the hacker managed to tamper with block 0, usually the attacker would not be able to find different block 0 with the same hash. Okay, so the hash would be different. If the hash is different, the hash stored in block 1 would be different different block 0. And by comparing the two, comparing the hash stored in block 1 and calculating the hash of block 0, anyone should be able to detect tampering. So the attacker, in this case, the attacker also needs to hack block 1 in order to include the hash of block 0. But if the attacker tampers with block 1, now there is a hash by comparing the hash stored in block 2 and calculating the hash of block 1, anyone would be able to see the difference. So now the attacker also needs to tamper with block 2. And to many people, the following association helps. It's a Hanoi tower. I don't know if people are playing this game in. So in Hanoi Tower, or Tower of Hanoi, it's very easy to move. You go down, more and more. The same happens with the ledger. It's relatively easier to hack the latest block. As we go back, it becomes progressively, exponentially more difficult to tamper with the blocks. And that's the meaning of immutability property of blockchain. And as mentioned, the only allowed operation is to append new blocks at the end. And that operation requires Byzantine consensus agreement between all the participants. So we talked a bit about Byzantine agreement yesterday. So this kind of agreement is needed in order to append new blocks to the blockchain, which also contributes to the immutability and security. On the other hand, blockchain is not without its new challenges. So let's talk about the new challenges introduced by blockchains. Compared to databases, it is slower. It has a lower rate of transactions. It takes the storage is less compact and more expensive. The second challenge is that technology and even standards, even terminology are still developing. So the technology is not mature yet, and things are changing from version to version. So it's difficult to maintain applications. Next issue with, or challenge with blockchains is public perception. So it's like every digitalization, right? So there is a switch to the new technology. There is a certain level of distrust in the technology, especially if, coming from non-technical people. Also, there is an issue with the lack of recipes and design patterns. Suppose I want to build a new application on blockchain. How do I approach it? Because in software engineering, there are well-known design patterns, right? They have been studied and established over the years. So, but that's general, and there are general principles. But specifically for blockchain, so which data should I put on blockchain? How should I approach interoperability? How should the component of blockchain storage and the component of non-blockchain storage interact with each other? Are there certain recipes? Well, the answer is recipes starting to emerge, but they are not there yet. There are individual smart contracts, but how do I combine different smart contracts together in my application? So obviously that hinders the development of applications. And therefore, up to this moment, there are no large integrated platforms on blockchain. And there are additional challenges related to smart contracts. They're prone to bugs, so programming smart contracts is a bit different from normal programming. There are certain things you need to watch out for, which you are not used to if you are just developing programs. Another challenge is state machine execution, which means that each contract is performed by every node. For example, in order to verify the correctness. Okay, if that happens, suppose like the contract performs some irrevocable action, or maybe non-idempotent operation, meaning that you can only perform the operation once. That's a problem, because if every replica performs the contract, then every replica would perform that operation. For example, there was a contract in at an installation in a hospital, where the contract would say, call firefighters, right? Okay, then if the contract is replicated, then there would be multiple calls to firefighters. And if a contract interacts with the external, not blockchain service, which is typically the case, this service needs to be designed with blockchain specifics in mind. So that takes some time to both develop correct interactions and to adapt. So here you can see some, in this slide you can see some recipe, or some block diagram, which answers the question, should I use blockchain, and which type of blockchain I should use? The diagram is a bit oversimplified, doesn't answer all the questions I would. But so, first question, do you need to store a state in your application? If you don't, then you don't need to use blockchain. If you need, then how many entities, how many players, how many organizations will update the state? If there is only one, then you don't need to use blockchain. Multiple, then the next question is whether we can use a trusted third party. Because that's, in practice, that's a big question. Many blockchain applications can be just put on the cloud, right? So you would lose some benefits. You'll need to pay to the cloud provider, but you may get better performance and scalability. So it's not a clear trade-off. So there exists some censorship-free distributed dApps on an open cloud. That's another emerging trend. So dApps, not all dApps need to run on blockchain. So obviously, another question you find is whether you can trust the provider with regard to privacy. Sorry. Okay, next question would be, okay, suppose you decided against using the trusted third party. Then the next, do you know all the entities who would be writing to the ledger? If the answer is no, then you should use permissionless blockchains. the answer is yes, now the next question would be, are all writers trusted? And if the answer is yes, then again, you don't need to use blockchain. If not all writers are for public permission, depending on whether we need public verifiability or not. Okay, now let's talk a bit about the blockchain reference architecture. So in computer science, we like to decomponentize big systems, right? To break it into blocks, into functionalities, components, and in many cases into layers, like the layers of communication. We do the same with blockchain. So the reference architecture breaks blockchain into layers, from the bottommost to the topmost. And okay, so let's go by layer. Hardware layer. Well, most blockchains do not need any hardware. However, dedicated hardware is still used for a number of reasons. The first reason, of course, is ASICs, mining. So, or maybe dedicated GPUs. So miners, we are going to talk about mining in the next lecture, but miners you can do mining on a general purpose machine. But it would run faster if you have dedicated hardware, dedicated chip, or dedicated GPU. The other use of hardware could be for ensuring privacy or security. And there have been some works to this end. For example, trusted execution environment. How many of you are familiar with trusted execution environments? You can raise your hand just to see it. Okay. So I'll explain what it is. The concept is quite simple. Suppose I do some calculation on my machine, and then I send you the result, and I'm telling you, okay, this is the result of the calculation. Well, you don't know if you can trust me, right? How do you know if this is the correct result or not? Well, so the fundamental question would be trust in me or in the entity that provides the result. So what's the idea? The idea is that I buy a machine, but in that machine there is one chip to which I have no access. And that chip can be provided by Intel, for example, or AMD, by a company. And that chip performs the calculation and signs the result, provides digital signature on the result. And even though I own the machine, I have no control over what this chip is doing. Well, okay, not exactly. I can ask the chip to perform the calculation. In that sense, I have the control. But I cannot tamper with the calculation. And I cannot tamper with the result of the calculation because of the digital signatures. So now, instead of me sending the result and saying, okay, this is correct result, please trust me, I send a result signed by that chip. Would you trust it then? Well, okay, now you need to trust Intel instead of me. Well, I mean, usually most people would prefer to put their trust in Intel, right? Instead of like every computer owner on Earth. So that's the idea of the trusted trusted execution environment. And in blockchain, there are quite a few uses of integration of blockchain with trusted execution environments. So again, here you need a hardware support, so it's the hardware layer. Next, up the stack, we have data storage layer. Data storage layer is how the data is laid out on disk. Okay, so we have blocks. How is each block represented on disk? How do we search for the blocks? How do we index the blocks? Do we just put the data in files, or do we also use some kind of database or key value store? So this is the concern of the data storage layer. Next, we have the communication layer. As we said, every blockchain system has a network associated with it. There are multiple nodes, and those nodes need to communicate. How do they communicate? Using what protocol? What are the operations of the communication? What's the topology of the network? All those are concerns of the communication layer. Data manipulation layer is mostly about consensus, but it's also about how do we validate blocks and individual transactions. How do we create the current state? So these are the concerns of the data manipulation layer. On top of that, we can build contracts and business logic. So the contract layer is sometimes also called the business logic layer. And of course, on the top, we have the actual applications built on top of blockchain. So this is how the functionality is broken. Now, why is it so important to break a big blockchain system into individual layers? There are several reasons to that. One reason is, of course, better understanding, because we can focus on implementation of one layer at a time, while just sort of abstracting away from the other layers. But there is more to it. Hyperledger, for example, has a very important plug-and-play feature in which you can implement. You take a system, you take one layer, and even each layer can be broken even in smaller components, and you implement, you provide a different implementation for a layer, while leaving all other layers intact. So in Hyperledger, the idea is to do exactly that. And by the way, upper layers in blockchain capture application semantics, while lower layers are concerned with technical system design. So this is the end of this lecture, and I'll be happy to hear your questions if you have any. Sorry, okay, the second sentence?
Yes, you talk about the new challenges
Mm-hmm.
which are being used as part of the operating technology.
Yeah.
Leadership respects. Can you suggest any different way? Next slide.
What was it? Next one.
Yes, new challenges introduced by the office. Can you suggest different ways to just mitigate or minimize these challenges?
Well, it depends which challenge, right? So which challenge would you like to focus on?
So as the technology is getting evolved
of course, regarding scalability, for example, I believe tomorrow there would be a lecture about the different scalability approaches. So we'll see how the technology has been progressing over time in that regard. So new ideas are coming out all the time. It is becoming better. But you know, like, so it's a bit like a balloon. You can sort of pump more air into balloon, but you cannot make it very, very big, right? So the barriers are being improved. So, for example, initial BFT protocols were deployed on a very small number of nodes. And actually, like in Google, like all Google is served by fewer than 10 servers running consensus. All of the Google infrastructure, fewer than 10 servers. Even though they have many, they have maybe like hundreds of thousands of servers in total, but only a small number running consensus because of the scalability barriers. Of course, like in general, BFT protocols were known not to scale maybe beyond 30 participants. But now, like in the new versions, they pushed this boundary to maybe 100 servers. But still, like, okay, so it's getting better, but it's still not the scale you could imagine. So, okay, so how do we deal with that? So you do not run consensus between, you have a system with 1 million participants. You do not allow all of them to run consensus. You select committees, you select representatives. Okay, how do you select committees? How do you select representatives? The system are getting better in that regard.
One more thing, worldwide different developers, contributors, they are having their own contribution in the development of these solutions for cognitive control, right? So can we have a common reference model which is worldwide adopted?
So a common reference model for what exactly?
So that will be the expert to have these solutions.
It will be more close to other things.
Just like to this right, we have that reference model which will be used in development of cognitive solutions. Just like any kind of a standard which has been adopted.
Well, it's more like the general knowledge is like being developed because every like designers. I've been working with designers of some blockchain systems, right? So they're always looking over the shoulder what the others are doing, and they're trying to understand the advancement, right? That's a common trend, and in that sense, like that, I think that the general, like the cutting edge knowledge is moving forward, yes, but it's more about understanding what you can do and what you should do, right? Because ideas come in all the time, but understanding which ideas would work and which would not, this is the tricky part, right? So, so that understanding is being improved. And of course, there are libraries, like at the basic level, for example, smart contracts, you are getting new libraries, right? So now you don't need to develop every smart contract from scratch. You can just take it from the library. It's getting better in that regard, absolutely. But still, like integration of everything. Well, okay, so in Hyperledger, there is what's called Composer. One of the projects under Hyperledger is called Composer. With Composer, you take different components and try to make sure that they play together nicely. Right, so there is a tool, and that tool is developing, right, it's being improved in that sense, so it's becoming easier and easier. But it's more of a like long, arduous, incremental process instead of a giant leap all at once. So yeah, we have a lot of competing blockchain systems. Is there a practical way of doing what exactly? Right. Okay? Actually, interoperability has many interesting questions. I didn't even mention some of those. Okay, suppose I developed a smart contract for one platform. Can I easily port it to the other platform? So, okay, it's probably not a good idea for me to jump forward too much and start talking about smart contracts at this point. But yeah, okay, at this point I can say that Ethereum was the first to propose the framework of smart contracts, and today many other systems, even if they propose their own idea of smart contracts, they still consider the question of how smart contracts and those new systems can run on the Ethereum platform, because there are advantages to that. So that's one aspect of interoperability I didn't, or maybe portability, which I didn't touch upon. But yeah, regarding different bridges, yes, this is one of the hottest topics. And the question of atomic swap. So if you look at, say, submission of papers to conferences, significant fraction of new papers would be on that topic. So, understood? Uh, it's like always chasing the tail, in the sense that the system is developing, right? So the bridge which was working well for the previous version now needs to be updated, right? So there are a couple of industrial projects on bridges, right? So which are well maintained over the time and which seems to be very active, right? So, so I believe that those bridges are already sufficiently mature and they are commonly used. Do they provide all the features? No. Do they connect all different cryptocurrencies? No. For example, Hyperledger and Ethereum are so Hyperledger Fabric and Ethereum, their concepts are so different that we will never be able to bridge. But it's okay because they are developed for different models. So there are very few cases when we want to bridge. So they are not really competing because like each one is targeting different applications and different models. And another interesting question is cross-system benchmarking. So there have been some attempts to create some benchmarks by which we can compare different systems. But okay, again, like different systems using the same model. So, so there have been also some progress and maturity in that direction, but it's not final. All right, then we'll end this lecture and we'll continue next time. All right. Let's proceed with the next lecture. So now we are going to get technical. The next two lectures are going to be on the intrinsics and the mechanisms of Bitcoin. So we'll start with the transactions, UTXO, blocks, and block mining. And we'll proceed with the other issues in the next lecture. So Bitcoin transactions. All right, so in this example, you can see three different transactions. Each transaction has inputs and outputs, which are encoded in a certain way, right? And the input to a transaction can only be derived from an output to a previous transaction, which is well known to everyone and which can be verified. So each user possesses a wallet identified by public-private key pairs, and the wallet can also produce such pairs. That's the idea of wallets. Then, suppose there is transaction A which makes a transfer and the output of transaction A is used by transaction C. So transaction C wants to use the previous transfer of transaction A as the input to this transaction. So what does the user of transaction C, the originator of transaction C, do? The user would encrypt transaction C using the private key produced by the wallet. Now, transaction C contains outputs to wallet addresses and in Bitcoin, every transaction must include one output, which is transaction fee. Transaction fee is paid to the miner who includes the transaction in the block. And we are going to talk about transaction fees later today. Now, transaction C must reference unspent transaction output. Is a very important concept in Bitcoin and other cryptocurrencies. To understand UTXOs, unspent transaction outputs, from previous blocks. So for every transaction, there are multiple inputs and multiple outputs. So what does it mean? Suppose I don't have as a user, I don't have a balance. It's not like a bank. Instead, I have a collection of assets. Could be a collection of Bitcoins, could be a collection of NFTs, could be anything. So for financial transactions, like amount of Bitcoins, as the inputs for my transaction, I can take, for example, certain amount. Okay, so in this example, the output 2 of transaction A is 1 Bitcoin, output 1 of transaction B is 2 Bitcoins, right? So I take both of them as the input. So the total amount of inputs in transaction C would be 3 Bitcoins. Now, the total amount of inputs must be equal to the total amount of outputs, right? So what does transaction C do? Transfers 2 Bitcoins to Bob, 0.9 to Carol, and 0.1 is a special transaction to pay the fee to whoever is going to mine the block. That's why the address is not specified here to whom it's transferred. Because at this point, when you create the transaction, you don't know which miner is going to include your transaction in the block. So you don't know to whom you are going to transfer the fee. So again, very important that has not been spent already. Otherwise, it's called double spending. And therefore, the system needs to track all the outputs that were previously issued, but that have not been spent yet. Because only those outputs can be used as inputs to new transactions. And once spent, a transactional output cannot be used ever again, because miners verify every transaction. So that's the idea of UTXO, and that's the basic idea of how transactions are structured and laid out in Bitcoin. So if you have any questions about transactions, please ask. Otherwise, we are moving on to wallets. The reference on unspent transaction part, which one? Yeah, so this, and therefore it can be used, therefore it's unspent, it's called UTXO, and therefore it can be used as an input to transaction C, okay? But now, after transaction C has been included in the ledger, everyone would see that this output has already been spent. So it's not a UTXO any longer. It's not an unspent transaction output any longer, right? And then it's impossible to reuse the same output ever again. So wallets and addresses. So users require a wallet to store money, and that includes any user. And now we can see a bit of a use of cryptography. So wallet is both authenticated and identified by public-private key pairs. Now, wallet can also generate its own key pairs. So many wallets have the ability to generate additional pairs of keys. Why is that? Because, for example, Alice wants to issue many transactions and sign those transactions, and Alice may want to receive funds from tokens from different other users. In that case, so what would be the address of Alice? It's not necessarily a good idea for Alice to reuse the same address all the time. Even though Alice is just one user, one person, Alice has the ability to generate many addresses, and each of them would still belong to Alice. So the wallet of Alice can generate many pairs and many addresses. They're called one-time addresses. So for each incoming transaction, so Bob wants to transfer some amount to Alice, Bob would ask Alice, what's your address to use for this transaction? That would be done out of band. Okay, and then Bob would use this address, but it would be just a one-time address. After that transaction, the same address would never be used again by Alice. Why is it a good idea to generate new addresses all the time? because this way, this promotes unlinkability. This way, other users are, I mean, the ledger is open and readable to anyone. This way, no one would be able to establish that the funds were all coming to the same address and belong to the same person. The pairs are generated using elliptic curve cryptography, as we discussed yesterday. Also, an interesting thing is that the wallets themselves are not part of the Bitcoin infrastructure. Bitcoin doesn't concern itself with how you generate those pairs. It's an added component, which is not standardized in Bitcoin. But of course, there are many solutions. And okay, so many solutions. Of course, you can keep wallet as a local application. You can run it in the cloud. You can have a hardware wallet, the picture of which you can see in the top on the right. Okay. There are also different types of wallet. There is custodial wallet and non-custodial wallet. Custodial wallet means that you trust that some third party to manage your keys. Well, that's a bit dangerous, right? Because it requires trust in that third party. And non-custodial wallet means that basically you have full control over the wallet, and whoever provides the wallet, for example, in the cloud, doesn't have access to your information. Okay, it sounds like it's better to trust yourself than someone else. Well, the problem, of course, is that if you lose the key, it's a problem, right? So do you trust yourself to never lose a key? It's not so simple, right? But I'm going to talk about it. Okay, so how do we redeem transactions? Each transactional address, and that's important, each transactional address, so what is an address of Alice? So each transactional address is a hash of the public key of the receiver. So what happens is that the wallet generates a new pair of public-private keys, then takes the public key of the receiver, applies the hash, and that hash becomes the address of the receiver. And the receiver needs to, of course, to sign the proof with the private key in order to redeem the transaction. If Alice is able to sign so after Bob transfers some funds to that address, Alice needs to show to everyone that she owns this address. How would she do that? Well, she is able to sign that address with the private key, and everyone else would be able to use the Alice public key to see that indeed that's the correct address. One interesting thing is that transactions in Bitcoin do not have the from address. So no one is able to know who exactly sent the funds. Well, that's not exactly true, because everyone knows that the funds correspond to basically the funds correspond to some previous UTXO, right? So it might be possible to track it. And even though there is no from field in the header of the transaction, there is still the signature. So if you manage somehow to track the signature, then you might be able to establish. And so you might be able to prove that you are actually the sender of the funds, because only you can produce the signature. But that's not as simple as just to see the address of the sender. So it requires some procedure. And as mentioned, each address is designed to be single use. Now the fun part, what happens if you lose the private key? So loss of private key means that the wallet and its funds are permanently locked. It's not longer possible to sign proofs redeeming existing TXOs. Since Alice is not able to produce signatures any longer, well, it means that everything that was transferred to the wallet in the past is no longer accessible. So you can say poor Alice, of course, but it's not bad for, it's not only bad for Alice, it's actually bad for the entire system. Why so? Because the money is lost, and thereby the total amount of currency in circulation in Bitcoin is also reduced. And Bitcoin wants to regulate the total amount of currency. And of course, if everyone starts losing funds, then it's a problem for Bitcoin as a system, not just for Alice. So trusting an online service to store your keys is also risky, since there is no way to prove that you are the rightful owner if the key is stolen or misused. There is no, apart from the keys, there is no other mechanism. So, for example, okay, one problem, of course, is the third party itself steals the keys from you. But another problem is if the third party is hacked and someone else stole the key and uses the key to redeem your transaction. That's it. There is no way for you to restore the funds. So yes, it's a big problem. And in practice, probably what's generally considered the most reliable solution is to store your private key on tamper-proof hardware wallets, such as this one. So, and of course, like you need to be careful with how you handle the wallet. So, how you where you store it in your house, right? And of course, that there have been some cases of physical abuse when it comes to the wallet. So it's not like 100% proof, but still it's considered an overall safer solution. Yeah, I can tell you a couple of just interesting stories about losing the key. So there was a famous case, like I believe in the UK, when a person bought a lot of bitcoins when in 2009, when it was still very cheap. And today, like the total amount would be over $100 million. What was the problem? However, he was replacing his computer, and accidentally, well, apparently he was a rich person, so maybe he wasn't involved in all detail. Apparently, he stored all the keys on the hard disk, and then the whole computer went to some dump, right? And since then, the person dedicated his life to wading through municipal garbage dumps and trying to search for the disk. He even offered to the $20 million to the municipality in order to help him to recover the disk. But so far, like his lifetime search is still continuing. I mean, the other story a bit closer to home is that I had a student, his hard disk got corrupted, right? And he was very sad. So I was compassionate because I thought he lost all the research results together with producing. But it turned out that he stored some keys there. All right. Let's talk a bit about the blocks. So far, we've talked about transactions and wallets. Let's talk about blocks in Bitcoin. So what does a block contain? So here you can see the chain of blocks, nothing new here. But let's consider the structure of a block. What does it include? As mentioned, each block consists of two parts, block header and block body. Block header includes some control fields, while block body includes transactions. So in the header, you will have several fields. Not all of them are depicted here. These are just maybe some of the most important ones, but there are more fields like the magic number, the version number, and so on. I'm not presenting all the fields in the header, just perhaps the interesting ones. As mentioned, there is a pointer to the previous block for the sake of immutability. Additionally, there is a timestamp when the block is produced. So you cannot produce, for example, if you send a block, propose a block with timestamp well in the past, the block would not be accepted. Actually, timestamp is not so simple because the clocks on different computers can be a bit out of sync. Your time, the time on your computer is not the time on my computer. So how can I verify? So suppose I receive a block with the time which is a bit in the past. Okay, should I accept it or not? Well, okay, so usually it's out of sync up to maybe a minute. But if you allow the blocks to be out of sync, say for 5 minutes, it's usually not a problem. But anyway, it's also a challenge and not a trivial one. Nonce is something related to proof of work, and we are going to talk about nonce and proof of work a lot today. So I'm not going to explain it in this slide. You'll have to wait for a few slides. Now, transaction root is a very important part. So, as mentioned, this is the header, and this is the block body. And here we have all transactions included. But we organize transaction as a tree. It's called a cryptographic Merkle tree. And then we have hashes. I'm going to talk about Merkle tree in detail today in the next lecture. But the idea is that we compute hashes throughout the and then we compute the root hash, and the root hash is included in the header. So the body only includes the transactions themselves. It doesn't even include the intermediate hashes. The intermediate hashes are only needed in this case for the computation of the root. So we have a list of transactions in the body, and the tree of the Merkle tree included in the header. So I can already say that one of the purpose of the root is for verification. Again, it's like a CRC to verify that the transaction included in the not be perfect. So those are perhaps the most important fields in the header. Next, we are going to talk about communication in Bitcoin, the communication layer. So in Bitcoin, the idea is relatively the primitives of communication are relatively simple. We just broadcast information to the entire network. Okay, what kind of information? New transactions, so clients who produce new transaction and want their transaction included in blocks, they broadcast new transaction to the entire network. Miners who manage to solve crypto puzzle and who propose new blocks, they broadcast those blocks to update the blockchain. So in both cases, it's the same broadcast primitive which is used. Now, how is this broadcast primitive implemented? It's implementing using what's called a gossiping protocol in a peer-to-peer network. So how does it work? I'm not going into the detail, just the overview. So first of all, there is like broadcast protocol. It's through gossiping. So every node in the network has a few neighbors, and every node selects a subset of neighbors to which it would send the new information. And when another node receives the information, it would also select a subset of neighbors to which it would send the information. And this is how it propagates. So of course, it's important how you select that subset. So there are a lot of details, but I'm not going into those details. There is also another element of the communication protocol. The broadcast is not always 100% reliable, so it's not a guarantee that the information would reach all the nodes. It would normally reach a large percent of the node, but not necessarily all the nodes. Okay, so how would the nodes who missed the information, how would they retrieve it later? So what happens is what's called the anti-entropy protocol, in which I exchange information with my neighbors. I'm telling them what I know. I produce a bitmap of information that I own. I don't send all the information that I have. Instead, I produce like a digest, a bitmap of the information that I have. And then like I exchange it with the neighbors, and the neighbor sends it to me, and we compare what the neighbors has and what I have, right? So this way I can say, okay, I am missing this transaction, and the neighbor can see, oh, I'm missing the new block. Okay, so now we can help each other. Or we can retrieve, we can ask to send the specific information which is missing. So the protocol, the gossiping protocol used for the broadcast in Bitcoin is not terribly efficient, but the thing that is, it has not been a bottleneck so far. So why is that? Because it takes an order of 10 minutes on average to create new blocks, to solve crypto puzzles, to perform other operations, and on average it takes much less than a minute to propagate the information. So 1 minute compared to 10 minutes. So yes, we could optimize it better, but compared to 10 minutes, it would not be a great improvement. So, despite the inefficiency, the protocol works also well because financial transactions, the transfers are very short. It's like, a typical transaction in Bitcoin would be less than 1 kilobyte, not megabyte. And also, the transaction in Bitcoin is far below that of credit cards, as we'll see. So, the implementation of the broadcast needs to be fairly reliable for the system to work, but 100% reliability in message delivery is not guaranteed. And message propagation should be reasonably fast compared to the time to produce blocks. Why is that? Why is it so important? Well, of course, you'll be able to get quicker confirmations for inclusion of transactions. But also slower network quantifiably increases the risk of attacks. So there have been some attacks on the network in Bitcoin. That's why it needs to be reasonably fast, But even an order of half a minute is still okay compared to 10 minutes. So this is just a very brief overview of the communication. Now, let's talk about the transaction flow. Suppose Alice wants to send some funds to Bob. What happens is that Bob generates and sends a public key address. Alice creates a transaction using this address. Alice signs the transaction and sends it to the network. So the transaction is broadcast using gossiping. Now, finally, some miner would decide to include the transaction in a block and propose the block, and the block would be appended to the chain, at which point Bob can verify that the transaction is in the ledger, and at this point, it becomes part of the UTXO, and from this point on, Bob can sign new transactions which would redeem this address. Okay? Now we start a relatively big topic, which is consensus in Bitcoin. How do we reach it? Okay, so consensus is about agreement. What do we need to agree on? We need to agree on two things. First, which recently broadcast transaction would go into the blockchain, but also in what order. The order is also important. Imagine you have double spending, so someone tries to use the same funds, so it's not possible in the real world. If I have like if I have a bill of 100 rupees, I would not be able to spend it twice. In the virtual world, however, I can send two different transactions. I can create two different transactions which would try to spend the same UTXO. That's not a legal thing, of course, but I can try to do it, and there are many attacks related to that. Okay, so in that case, if it happens, it's very important to know which of the two or multiple double spending transactions is the first one, because the first one would be legal and the second one would be illegal. So the order is important. All right, so how do we reach consensus? The general anatomy of consensus, of all consensus solutions, is like this. Someone needs to make a proposal, everyone needs to reach a consensus, and then, of course, the decision needs also to be announced and needs to reach everyone. The problem, however, is that reaching a consensus is a tough problem, and especially in an uncontrolled environment without any entity controlling the outcome. And there are dozens of impossibility results since 1983. It doesn't scale well beyond order of 30 participants, right? And it takes a long time to converge. So everyone would converge to the same decision. So that's not a good news, right? And yet, so I would say that Bitcoin was the first practical system that manages to reach consensus on a large scale. So let's see how it does it. So the first challenge is who proposes new blocks and when. And that's the critical part. The network cannot sustain. Consensus protocols are fragile. They are not scalable. So the network cannot sustain each and every user of the system making a proposal whenever the user wants. We need to moderate it. We need to make sure that the rate of proposals, we need to moderate both the number of proposals and the rate of concurrent proposals. The problem is made worse by the proliferation of identities, Sybil attacks. Because now, one user, so again, it's not possible in the real world, but in the virtual world, I can create multiple identities of myself, and now 10 different Romans, well, no one would know that it's Romans, right? 10 different miners, 10 different proposers would suddenly, each one propose a block. Okay? That's a Sybil attack. When one entity replicates itself or creates multiple identities for itself. So that exacerbates the problem of scalability or moderation in blockchain. So again, we need to moderate both the number of proposals and the rate of concurrent proposals. And we need to do it. Programmatically as a mechanism. There is no organizational entity or censorship. So it's all done by mechanisms. On the other hand, we need to keep both sufficiently high. Because the easiest way to moderate the rate is to say no proposals. Well, that's not a good system, right? So if we want to make progress. We want to sufficiently high transaction rate. So we need sufficiently high number of proposals, but we do not want the number of proposals to be too high. So we need different mechanisms. One mechanism to bring it down, one mechanism to bring it up. And Bitcoin includes both mechanisms. Okay, so let's start from the question of how we keep the number of proposals and the rate of concurrent proposals down. There are several principal solutions. I'm going to talk about them today. But Bitcoin uses a proof of work. What is proof of work? In proof of work, a miner, a block proposer, needs to do some heavy computation and show a proof of the heavy computation. And whoever manages to do the computation first would gain the right to propose a block. Well, everyone would gain a right, but of course, whoever proposes the blocks later, the block would not be accepted. Okay. So there are additional optimizations to improve the scalability. For example, why do we do blocks? Why don't we do consensus for each transaction separately? Can someone tell me why do we want to have blocks? We don't, in principle, we don't have to. We could have, we could run consensus for each transaction. Why would it not be a good idea? Why do we want to include multiple transactions in a block? Of course. Scalability. Again, it's scalability. So if suppose we have 100 transactions, and if we want to run consensus for each, and then we will have 100 times more block proposals or transaction proposals or consensus instances compared to the case when we combine all 100 in a single block, and then we just run consensus once. Much more scalable. So a block in Bitcoin is, as we saw, structured as a tree of proposed transactions with nice cryptographic properties, but we'll talk about it later. Okay, so let's talk about the crypto puzzles in Bitcoin. We said that in order to gain the right to propose a block, a miner needs to do some hard computation and show a proof of it. What's the mechanism? The mechanism is called proof of work. In Bitcoin, it's implemented by crypto puzzles. So in crypto puzzles, the proposal needs to find some nonce, which is a fixed size number, such that the hash of the block is included. And again, like the block consists of a header and a body, right? That's a block. So what we want is to find such a number to put here in the header that the hash of the block would be within certain numerical range. Specifically, it would be smaller than a target value. It would be sufficiently small. And there is theoretical proof that there is no good way to find such nonce. What we effectively need to do is to scan the entire nonce space one by one. Okay, we can choose the order in which we scan the space of candidate values. But that doesn't help. We cannot even know which region of the space would be more likely. As a matter of fact, in crypto puzzles, each point in the space of candidate values has the same probability to be a good solution. So we simply linearly scan values one by one, and that's the best we can do. So what is a target? Target is a fraction of the hash space. And if we make the target smaller, it would be more difficult to find successful solutions to crypto puzzles. If we made the target bigger, it would be easier. Another interesting aspect of Bitcoin is that Bitcoin itself regulates the target. How does it do it? Every node computes the target every certain number of blocks. So that allows for synchronization because all nodes know the target for a given block. They all in agreement about the value of the target. Okay, so we compute how? Such that the average time for the whole network to solve a crypto puzzle is 10 minutes. What happens is that the system profiles its performance. Everyone would look at how long it takes to produce blocks. If blocks are produced too fast, then the system would make the target smaller. So it would become harder to produce block. If the system is too slow in producing block, it would make the target larger. In such a way that on average, it takes for the whole network 10 minutes to solve. That means if you take a particular binary processor, then the mean time to next block would be 10 minutes divided by the fraction of piece computing power to the total computing power in the network, right? And another important part is that the solution is fast to verify. So how do you verify that it's a good nonce? You just compute one hash. Very cheap. One hash computation. But in order to find the solution, you need to explore this like a very large space of potential values. And this is where the hardness is coming from. So this is an illustration. Yeah. So here you can see a ledger including 3 blocks. And now the block number 3 is being formed, right? So each miner listens to incoming transaction which the miner receives for the broadcast, right? And maintains called the mempool, pending transactions. Pending meaning that need to be included in blocks, but that have not been included in blocks yet. So that's mempool. And but essentially it's a loop, which we'll see. All the time, the miner will try to form a block out of the transaction in the mempool, and then we'll try to explore different nonce values such that the hash starts with sufficient number of zeros is the same as to say that it's sufficiently small. And only when the successfully finds the nonce value, only then it would declare it as a solution, would attach the solved block to the chain and would propagate the block by using broadcast to the entire network, right? If someone else beats the miner to it, then the miner would update the pending pool of transactions, right? Would remove transactions from that pending pool, would try to form a new block which would already be block number 4 on top of block number 3. That's another illustration of the cycle of POW of Bitcoin. So there are 3 processes here which are happening in parallel. 3 processes. One process is that new transactions are coming all the time. And they're entering the mempool. And then from the mempool, they're being added to the block being proposed, right, being formed. So at any point, like before you solve the crypto puzzle, at any point you can add new transactions to the block. That's one process. The second process is difficulty adjustment. Okay, that doesn't happen very often. It happens on 2,000-something blocks, right? Okay, when it happens, the difficulty is being updated. And then the main process is this loop, right? The miner would select a new hash, starts from here, then would include the take a new nonce, would put the nonce value in the block, would compute the hash, would compare the hash to the target. Yes, is declared as a winner. No, it goes back to the non-selection. And the loop continues and continues. So the 3 things happen in parallel. This is how POW works. Now, you could ask, okay, you could ask a couple of questions. One question, are you even guaranteed to find the solution in the nonce space? The answer is no. There could be no solution at all. What happens in terms of probability, every point in the nonce space has the same probability to be a solution. But it doesn't guarantee that collectively, collectively the nonce space may include many solutions or 0. It's all probabilistic. The second question you can ask here is, suppose I started this loop, right? I already have a significant fraction of the nonce space. I have not found a solution yet. At this point, new transaction come. Is it a good idea for me to add new transactions to the block and alter the block? Because maybe if I do that, maybe that would change the nonce space. I would need to change the nonces again. So maybe it's a bad idea for me to put in new transactions. The answer is no. And that's the beauty of how it's done in Bitcoin. And the reason why it's okay for me to add new transactions is, again, probability distribution. So regardless of the mining process is memoryless, the probability for a point in the non-space to be a solution doesn't change as I explore solutions. Suppose the non-space includes like 10 points. I explored 5. Does it affect the probability for point number 6 to be a solution? No. It's a memoryless process. And because of this, if I add new transactions, it's still the same probability. The probability is not affected, and therefore, the miners are incentivized to add transactions as they mine. So that's an important problem. So, okay, that was the challenge of keeping the transaction rate down. And now what's like, we had the second challenge. How to keep them up? And why would the miner propose non-empty blocks? In order to incentivize miners to propose blocks and to include transactions, we have two incentive-related mechanisms in Bitcoin. The first mechanism is called block creation reward, and a block proposal creates a number of new Bitcoins and transfers them to the proposer. It's called the coin-based transaction in Bitcoin. So it's included as a separate transaction in the block. And by the way, it ensures that each proposer solves a different safety puzzle because every miner would put a different coin-based transaction in its block. It's the only way in which new Bitcoins are created and added to circulation. And the amount is predefined, so the proposer cannot decide how much it would get. The amount is fixed, and it gets halved every 210,000 of blocks. So you can see that it's a geometric progression. And it's predicted to go down to 0 before year 2140, but of course it's far in the future. Who knows what will happen by then? The geometric progression totals to 21 million Bitcoins. So that would be the maximum amount of Bitcoins in circulation, minus all the Bitcoins that were lost due to lost keys. However, there is a catch. The catch is that the Bitcoin reserved the right to change all the rules in the future. The same consensus mechanism is good not only for proposing new blocks. The same consensus mechanism can also be used for voting on new blocks. For voting on new rules. So instead of geometric progression, the Bitcoin can suddenly decide to do something else. If everyone agrees to switch the rules, that's good. The second incentive mechanism is called transaction inclusion fee, in which Alice can decide to pay a small fee to the block creator as part of her transaction. This is very different from block creation reward. It's voluntary. There is no fixed and predefined amount. It's at the discretion of Alice. Alice decides. Now, of course, if Alice decides to put a very small amount, maybe miner would not like it, and maybe miner would not include Alice transactions. So Alice has a certain risk here. And generally speaking, the miners would prioritize transactions with higher fees, right? So due to those incentives, miners do want to propose blocks. Due to POW, they don't propose too many blocks. So by the way, there is a common misconception that POW is the consensus mechanism in Bitcoin. That's not exactly true. POW is not how we reach consensus. POW is the mechanism protecting consensus. So the two incentives create what's called the crypto economy of mining. They give rise to the mining industry in Bitcoin. The miners, this is what they do. They are cracking crypto puzzles and listening to transaction broadcasts. So there is a dedicated rig. They should do that. Okay, so is it profitable? Well, there are quite a few miners, so apparently yes. But what can we say about this crypto economy of mining? There are expenses. The expenses would be to buy the mining rig, and there are operational costs like electricity, cooling, and repairs. The expenses are paid in real currency, while operating costs are variable. On the other hand, profits. So what are the profits? Block creation reward and transaction fee times the number of transactions in block. So the profits are paid in Bitcoins. So how profitable it is depends on the number of, depends on the ratio between the real currency and Bitcoins. However, the fee and rate of transactions are unpredictable. And while the mean time to next blocks is easy to compute, the per miner sample is small, while variations are huge. So you're a miner, you have a mining rig. You can be lucky and find the jackpot next day, or you can spend all your life, 100 years, without finding anything. So there is this unpredictability. And therefore, because of this unpredictability, there is a concept of mining pools. It's a group, what is a mining pool? It's a group of cooperating miners. If one miner in the mining pool finds the solution, the miner would need to share the profits with everyone within the pool. Okay, so it means that the jackpot becomes smaller, but because of the size of the mining pool, you're also more likely to hit it. So it becomes more predictable. The winnings are smaller, but more predictable. And usually people say it's a good trade. I suggest that we stop the lecture here and continue the next hour. Testing. Hello, hello. Okay. All right, so so far we have been talking about the crypto economy of mining and about basically how to keep the rate of proposals down, but how we keep it up. But we have not talked about consensus itself yet. So how do we do it? Okay, so the basic idea is simple. A miner broadcasts the proposed block, and the block includes a hash to the latest block known to the miner. When another node receives proposed block, it would verify several things. It would verify that the proof of the crypto puzzle solution is valid by calculating one hash and comparing to the target. It would check that each transaction in the block is valid using business logic. And it would also check that the hash pointer is valid, of course, to the previous block. And then if all those conditions are satisfied, it will append the new block to the local copy of the blockchain. The problem, of course, and this is the problem of consensus, is that local copies may diverge. How? Because of lost messages, but also because competing blocks arrive in a reverse order. Imagine that two blocks were produced, blocks A and B were produced almost the same time. Then one node may receive first A and then B, and another node may receive first B and then A. And usually what happens is that, like, okay, it doesn't matter how exactly we do the order. The problem is that locally, a node is not able to determine the correct order between A and B. So the probability of those bad scenarios depend on the network, but they definitely occur. So this is what the consensus problem is solving, right? And this is the critical part. The consensus is resolved by conflict resolution rules. If the proposed chain is longer than the current local copy, then we abandon the local copy and replace it with the local chain that's coming from the network. If the new chain, if the proposed, if what I receive from the network is the same length or shorter than what I already have, I do not replace, I ignore it. So it's called the longest chain rule. And that's the conflict resolution rule in Bitcoin. So why does it solve consensus? It provides probabilistic convergence over time when using the longest chain for conflict resolution. So we'll see an example in the next slide. So it means that blocks It means that the blocks are non-final. So when the block, suppose the block is accepted. And of course, all the transactions in this block are included. So, and then maybe the services are rendered. And then sometime later, a new block comes, and then another new block comes, competing with the current block. So we throw away the current block and replace it with a longer chain. That means that we do not converge. We put a block in the chain, but we don't know if it's final yet. Maybe it will be replaced in the future. How do we know? Well, we don't. We don't know for sure. The good thing is that the probability of a block being non-final decreases exponentially with the number of later blocks stored on the chain. So if this is the latest blocks, if this is the very latest block which I just appended to the chain, it's not unlikely that the block will be replaced in the future. However, if I get another block on top of this one, that decreases the probability that the block will be replaced. If I get 2 blocks later, the probability gets exponentially smaller and smaller. And it never, theoretically speaking, it never reaches 0. It halves, but it never reaches 0. But of course it becomes like, it can become as small as we want. Okay, so when do we declare a victory? When do we say, okay, the probability of replacement in the future becomes so small that we can say it's final? Because that question is important, because we need to know when we can effectively start rendering the services based on included transactions. So the standard Bitcoin clients declares victory after 6 blocks. So it's enough the block with the transaction is included, 5 more blocks. It says, okay, now let's say that the transaction is final. Why 6 blocks? It's totally a random number. It could be 5, it could be 7. Just 6 is good. It's big enough for the, probability to the 6 is small enough so we can say it's final. So, okay, so 6 blocks. On average, we say it takes 10 minutes to mine 1 block. So 6 blocks means 1 hour. It's not too bad for most purposes, but sometimes, like when you deal with large-scale vendors like Amazon, Amazon.com would prioritize transactional throughput. So 1 hour may be a lot of time for Amazon.com. So sometimes vendors prefer to risk losing the money, but shipping the services earlier. That happens. So so the interesting part is that there is a proof that, like in a large-scale system, for a period of time, so what happens is that there is a local copy. Every node maintains a local copy of the chain. So the prefix of the local copy is considered to be stable because it's like long enough in the past, right? But the suffix, the most recent blocks, those may still change, right? So then the chain grows and the prefix grows, right? So the stable part grows over time. And if transaction ever stop coming, there would be eventual conversions. Everyone would end up with the same chain. Okay, here's a graphical illustration. So this is like the common prefix. blocks 0, 1, 2, and, well, okay. The participants, the nodes, actually don't know that it's the common prefix. They don't know the situation on other nodes. But we, as observers of all the nodes of the system, can observe this is a common prefix. All right. So, and at this point, there are competing proposals of block number 3. They both build on block number 2, but they're different proposals. And they're proposed at around the same time. So there is a split in the network. Some nodes would temporarily accept branch 1, the first version of block 3. Some nodes would temporarily accept the second version of block 3. So there is a split. Okay, what happens next? The network, let's say half of the part of the network, would continue mining on top of branch 1. The other part of the network would continue mining on top of branch 2. So now there is a competition between the two branches. Okay, so let's say that the two versions of block 4 were also mined at around the same time. In this case, the split continues. And there is a group of miners mining on top of the first version of block 4, and there is a group of miners mining on top of the second version of block 4. However, due to the variance, and that's very important, like there is, we said 10 minutes on average, but in reality there is a distribution, right? So it's very unlikely that the two blocks would be found at the same time. And due to the variance, one group, one branch will find a block faster than the other branch. And when miners receive the valid blocks from a longer branch, they just throw away their own local branch. So, in this case, if branch 1 finds block 5 and branch 2, and there is enough time to propagate block 5 to all the miners also in branch 2, then all the miners maintaining branch 2 will just throw away their branch and adopt this branch because it's longer. So is it clear how it works? Okay. I'm just continuing with Bitcoin. More information on Bitcoin. So far we've covered consensus in Bitcoin, which was a heavy topic, right? Now let's talk about other aspects of Bitcoin. The Merkle tree. I briefly mentioned it. Now I'm going to go a bit deeper. First, how do we build a Merkle tree? We set transactions are in the leaves. Then we take a hash of each transaction, the next level of the Merkle tree. Then we take those two hashes and come it would be hash 0, 1. And similarly, we take hash 2 and hash 3 and compute hash 2, 3. The next level of the Merkle tree. Then the next level of the Merkle tree, until we finally compute the root hash of the tree, which is a combination of the hashes from the previous level. Okay, so this is how it's built. But why are we doing that? Well, again, one purpose is the verification of correctness, right? Data integrity. That's a clear purpose. However, to this end, we didn't need to build a tree. We could have taken a list of transactions. We could have computed the hash of the list and used that hash for integrity. So it doesn't answer the question why we build a tree. So the reason, the main operation for which Merkle tree is needed is what's called simple payment verification. So in Bitcoin, there are what's called full nodes and lightweight nodes. Full nodes maintain the entire ledger. Lightweight nodes don't have enough resources. Lightweight nodes have they could be mobile devices. They only have, say, headers of transactions or blocks. They don't maintain the bodies of blocks, only the headers, because they don't have the space. And the headers are much shorter than the bodies. Okay, so then they store information. So for example, if Alice send some funds to Bob, how would Alice know that the transaction is included? How Bob would know that the transaction is included? Normally, you would have access to the transaction, but if you are a lightweight node, if Alice and Bob both maintain a lightweight node, they wouldn't know. So what can they do? How can they verify the inclusion of transactions in that case? Well, what they do is they send a request to a full node that they know. But the question, can they trust the full node? So this is where the Merkle tree comes in the picture. So it's possible to create what's called a Merkle tree, a Merkle proof. Merkle proof is a proof of inclusion of a transaction. So let's see how can we efficiently verify inclusion of a transaction in a compact way. Let's say we want to verify inclusion of transaction 3. So we don't have all transactions. We only have which is included in the header, and we have transaction. How can we prove that transaction 3 is included in that particular block? Well, if we have transaction 3, we can compute its hash. Now, if we also have hash 2, we can compute hash 3. We can compute hash 2 free. And if we have hash 0, 1, then together with hash 2 free, we can compute the root hash and verify that this is the correct root hash. In order to do the verification, we need the following. We need hash 0, 1, hash 2, and transaction 3, which we have. We don't need the other information in the tree. We don't need tx2, we don't need tx1, we don't need tx0. We don't need those hashes. So if we have hash 2 and hash 0, 1, we can verify the inclusion of transaction 3 in the root hash. And it's very difficult to falsify, right? Because of the cryptographic properties of the hash function. So what happens is that the full node can send the lightweight nodes, like Alice and Bob in our scenario, can send just the proof, not the entire information in the block, only the Merkle proof. And that would be enough for Alice and Bob to verify the inclusion of the transaction. On the other hand, Merkle tree is not a search tree. So if you want to search transaction or data in the block, for that purpose, you wouldn't be using the Merkle tree. There is another reason, not advantage advantage of using Merkle tree. In Merkle tree, spent transactions can be pruned in the local copy, leaving only the necessary intermediate nodes to save space. What do I mean by that? Spent transaction means that like it's not UTXOs any longer. It's TXOs that have been spent. So imagine that all the outputs of transaction 0 have already been spent. In this case, we are not interested in transaction 0 any longer for that block. So we don't need to keep it in the copy, we keep its hash, right? We can prune it from the tree and save some space. And imagine that the outputs of both transactions 0 and transaction 1 have been spent. Okay. In this case, we don't need anything here, right? So this way we can save space in the storage, but of course someone would still need to keep full track of the ledger. So some nodes would still continue keeping the entire ledger, but some nodes would keep an abridged version. So that's the idea of the Merkle tree. Now, another point is about data manipulation and queries, or another aspect of blockchain, right? So far, we've been talking about how to update the ledger, but what about reading the ledger? So the ledger in Bitcoin is publicly available. There is no access control whatsoever. And not only this is further facilitated by services for querying the ledger, such as Blockchair. So there are some web services whose purpose is to provide a window into larger ledgers, right? So they extract information about individual blocks and transactions in the ledger. And in practice, a copy is held by many users. And users are encouraged to download and run a verification. So because of this, like this transparency contributes to better integrity of the data. So this transparency is definitely a boon for data integrity, but it's a challenge, of course, for privacy, because public keys are used as user identities, so it's not real identities. And a key can serve as a pseudonym. But the main, and as we mentioned, is user should use a different key for each transaction. The main threat comes from analyzing the history of transaction and linking them together. So we'll talk specifically about this topic when covering the Monero cryptocurrency that improves over Bitcoin in that respect. So tamper resistance is mostly a good thing, but the problem with tamper resistance is it's difficult to compact the ledger or prune the history. And let's look at what happens with the size of the Bitcoin ledger. Okay, it's from 2023, now it's bigger, of course. So it's growing. Half a terabyte is not too big, of course, today, but it's sizable, right? And the curve is linear. So up until a certain point, it was small, measure in small number of gigabytes, but now it's about a terabyte. It grows in a linear fashion. So it's not too bad. It's not too big. Again, the thing is that the transactions, financial transactions, individual transactions are very short. But over time, it accumulates. And it can never be compacted. So that's a challenge. Okay, let's talk about the the layer, the business layer, the smart contract layer in Bitcoin. It's rather primitive compared to the smart contract layer in later systems, but still it's interesting because it was first. So the output and the input have some scripts attached to them. The output of a transaction additionally includes a verification script which would represent the conditions under which the output can be redeemed, or in other words, included as an input in a later transaction. And a typical script in Bitcoin would look like this output can be redeemed by a public key that hashes to a certain value along with the signature from the key owner. And similarly, there is a redeeming script attached to the input. So both scripts are executed for the purpose of verification. And not only by the owners, but also by everyone verifying the transaction. The script language includes an order of 200 different commands. The main focus of the script language is support for cryptographic primitives. However, it's an ad hoc language, right? So there is no even like a description of what can be achieved with it. It's definitely not a Turing complete language. There are a lot of things that you cannot do. You cannot do conditional statements, you cannot do loops, and many other things. So it's rather primitive. But it includes some efficient implementation of cryptographic primitives with focus on signatures and hashes. Now, we are going to spend a lot of time talking about security. So I don't want to talk too much about it now. However, there is this major classical problem of double spending that I do want to discuss. So double spending is again due to the fact that convergence of blocks in Bitcoin is probabilistic and only eventual, right? So for a period of time, there could be two versions of the same block. So imagine that there is a real chain. Okay, first of all, there are two transactions, A and B, and both transactions are transferring exactly the same UTXO to two different users, right? So it's a double spending. Now, there are two versions of the chain. First it starts with like a real chain. And in the real chain, in block number 10, there is transaction A. Okay? So the attacker, whoever transferred 1 Bitcoin to the first merchant would get some services after a while. Okay. And in parallel, in secret, the attacker built an alternative chain. And it would make sure that the alternative chain is longer than the current chain. Okay, so after the services are rendered, the attacker would disclose the secret chain to everyone. And at this point, the attacker's chain would replace the chain so far, and the secret chain, the attacker's chain, would include a different version of block N with transaction B included instead of transaction A. At this point, the attacker would get some benefit due to transferring 1 Bitcoin to merchant 2. So the attacker gets double benefit from the same fund, from the same UTXO. And that's called double spending. So this is like the classical attack in Bitcoin and similar systems, especially systems based on proof of work. It's also called 51% attack because in order to launch the attack, the attacker would need to overcome the current chain by proposing a longer chain. And to do that, the attacker needs significant computational power, at least 51% of the network. Now let's talk a bit about limitations of Bitcoin. So in what sense Bitcoin could be improved, and it is improved by later systems? Newer version. And the two versions are not compatible, right? So we have a partition. That's a fork. Another case of a fork is, say, the size of the block, right? So the size of the block is a constant subject of debates in cryptocurrencies. And suppose some users adopt new size of block, some users are conservative, continue with the old size. Again, we have a fork. So soft forks means that the newer version can still work with the older version. So users who do not update cannot work with the new version, but users who update can work with both versions. That's a soft fork. Hard fork means that the new version is not compatible with the old version, so it's complete partition. There is another related problem and another reason for fork creation. There have been some well-known instances where funds were stolen from Bitcoin, right? So a significant amount of funds. And it's not discovered immediately. For example, 1 month later, users discover that over the entire month, significant amount of funds were stolen. What do? We have two options. One option is to say, well, and continue. The other option is to roll back to cancel all transactions over the past month. And not just the bad transactions, not just the thefts, all good transactions too. Okay, this way you cancel the theft, but you also cancel the good transactions. Is it a good trade-off? Not clear, right? Not clear if it's a good trade-off or not. Again, there is a debate, and people disagree. Some people roll back, some people do not continue forward. We have a fork. And it's actually funny that a lot of forks were created this way. Those forks usually have some very fancy names, like Bitcoin Gold, right? Sounds very good. It was because of theft. So it's not a good thing. More limitations. So the transaction rate in Bitcoin is only 7 transactions per second. It's not so good. Compare that with Visa, where you have like 2,000 transactions per second on average. And it can even support more than that. So, okay, it depends on the block size, and again, there are a lot of discussions about the block size. Next, Bitcoin uses proof of work, and there is a reason why later systems abandon proof of work and prefer to go for alternatives. So the reasons are, the main reason is that proof of work, it doesn't benefit humanity whatsoever. It benefits the miner. The miner gets the reward, right? But the miner found a solution to the crypto puzzle. Well, that solution is not useful to anyone. And yet, the miner spent significant amount of resources and energy, power, in order to find it. So the environmental impact, it uses, despite the much lower throughput, it uses thousands of times more energy than credit card transactions. And we'll see comparable energy consumption is comparable to a decent sized country. Like if you take all Bitcoin miners together, they spend as much power as some moderate sized, well, not India, but moderate sized countries in Europe. There are also some minor disadvantages related to the bootstrap time for a miner. So what happens, like suppose new miner wants to join the system, it needs to download the entire ledger and verify it. Well, that process takes days. Okay, so let's see some charts related to energy consumption by country. Okay, alternatives to POW. Let's quickly go over the alternatives, and that will be the last thing for today. So Ethereum switched to proof of stake in 2022. So what is a proof of stake? In proof of stake, validator bids for the right to propose blocks by staking their tokens. And then, after different validators place their bids, a lottery takes place where the probability of being selected as the proposer is proportional to the stake you put. Well, that's definitely much cheaper in terms of the energy consumption. However, it's not a perfect mechanism either, right? So one issue is that if you don't have funds, then you cannot put a stake and you cannot become a proposer. So as a result, the rich may be getting richer, while the poor stay poor. The other problem with proof of stake, the other disadvantage of proof of stake is the issue with deposits, right? So the deposit, after the stake, the deposit is locked, and then it can also be locked for a period of time, right? So there is a question for how long. Should we return? Okay, so should we return the deposit immediately, or should we keep it locked for a period of time? We can keep it locked in order to make sure that not too many attempts, not too many stakes are proposed in parallel. So there are a lot of debates for how long to keep the deposit locked and whether it's a good idea. The next alternatives, well, it's not suitable for every system. It's proof of authority. In proof of authority, well, it's only used in consortium blockchain. So there are a few dedicated nodes which can decide together that, like, still not one node, but a few, and they do not necessarily trust each other. But they decide, they make all the decisions in the system. That's a simple one. The next alternative is quite interesting. It's called proof of elapsed time, and it's using the trusted execution environment about which we were talking earlier. So, node, say a miner, or a node who wants to become a proposer, would request a waiting time from a function running in the trusted environment. And that function would create some random time and sign it. And now everyone can place a bid with the shortest wait time produced by the trusted environment would produce the block. So that's the basic idea of it, right? And it's very fast. it can scale to thousands of nodes, and it can be quite energy efficient too. But of course, it requires trusted execution environment, which is expensive and not universally adopted. Yet, this idea of proof of elapsed time is used by Sawtooth, Hyperledger Sawtooth, and it's also used by Solana, which is a popular cryptocurrency. And of course, it means that you need to trust Intel, right? So you assume that Intel cannot be bought to favor some miner or some proposal, right? Okay, more alternatives. There are many more actually. There is order of 30 different alternatives. I'm not covering everything. I'm just giving you some taste of what exists, right? So proof of capacity. Proof of capacity, also known as proof of stake, proof of storage, requires that validator nodes commit hard drive space to increase their chances of producing the next block. So the idea is commit some space on the hard drive, like a deposit, right? So you deposit not only cryptocurrency, you can stake your resources. And the resources could be this space. So that's an interesting idea, again, quite cheap, and used in quite a few storage systems based on blockchain. Okay, so that's the end of the lecture today. Welcoming questions.